It's great to see the NDN Com again and the NDN community. It's always a pleasure to interact with you guys. I think this is my fourth or fifth meeting, so sorry I couldn't make it to Los Angeles to be with you guys. So I'm going to talk today about AI inferencing and how it creates a distributed data challenge and how NDN can help solve this big problem. Before I get started, DELL is in the middle of the AI revolution. We're working with customers today to build the largest AI infrastructures on the planet. It's a very, very large business for us. We've committed to Wall Street to deliver 15 billion plus this year of strictly AI revenue. So we partner with a lot of different players in the ecosystem, our semiconductor folks, independent software vendors, tooling folks, and a large variety of people that are making this real for folks. Okay, this is just a typical DevOps process, right? That AI is used in AI, right? You have a design phase, which you're developing hypotheses and based on an opportunity or a problem definition. Then you have a very extensive phase in data science and engineering. This is, finding the right data, making sure it's curated, it's normalized, that it's usable for the model, and that you have adequate coverage on your hypothesis so that you can train the models to do the right thing. Then development and training actually is a little bit easier. You have to design the architecture of the model, you have to do the feature engineering on the data, you have to select the right hyperparameters, and then you run tons of experiments tuning the model to, once you get it trained, to what you want it to do. And then staging and deployment is also or maybe the most complex phase, is taking it out of development and moving it into operations. Right? And then operating models are quite complex. This is what I would call more of a discriminative approach. Generative models use different tooling. You'll see a lot of reinforcement learning and other capabilities that are leveraged here. In fact, I had a slide I presented 3 or 4 weeks ago at NVIDIA GPU technical conference where I told everybody it's a trick question. I showed them a causal AI, from like symbolic days, reinforcement learning, discriminative AI, generative AI, and I said that this is a trick question. What's used to train a generative model? And the answer is all of those techniques. Causal techniques are required. Reinforcement learning is required. Discriminative techniques in ML, clustering, et cetera, is required, as well as this little thing called a transformer, which is the generative piece. So it's super complex, and it's very data intensive. You're curating data sets here. You're moving data sets around and training models here that have to be split up into validation, testing, and training data sets. Here you're actually moving models around and pipelining data, setting up data pipelines. And here you're actually executing things, something called inference in AI. Again, to why generative models are so data intensive. So generative models, the product that I help design and run is called an AI factory. And the reason we call them AI factories is they produce things called tokens. They consume tokens and they produce tokens. A token is a piece of a word, okay, or a patch of an image, or a snippet of audio. All right, and these tokens are fed into a process called embedding, where they're put into a vector database, okay, and then so you can do similarity search and some other things, right? When you take this little, largely usually less than 10 bytes and usually less than 4 bytes token and put it into this embedding space, you spread it across a whole bunch of dimensions. 1,000 is a very common one. They go all the way up to 3,072 and all the way down to about 256 dimensions. And each of those dimensions is a dense vector. So it is a floating point representation of one aspect of this token. So it's virtually incompressible, and it it is much larger. So you take 10 bytes and it becomes tens of kilobytes because those vectors are represented by 32-bit floating point. Okay, because they're dense and they're all clustered around 0. Okay, so they're fractional. They're not integers. Okay, so this massively expands the amount of data that you have to manage. And then on top of that, there's this thing called retrieval augmented generation, which has become really complex, where you basically have to give the model context. And so you create a library of content that when the prompt from the end user comes in, you include contextual information out of this vector database, another vector database sitting here with embedded representations to generate a response that has the correct context. All right, and then there's something that I'm going to talk about in a couple of pages that, you know, there's a lot of I/O management. All the prompts coming in are cached as objects. All the prompts going out are cached. There's a lot of processes that run out here called guardrails and memory, et cetera, et cetera. So, and it's getting much more complex with reasoning models. So you keep a lot of this data that's going to the model. So when you send something to ChatGPT, be very careful because it's being cataloged, stored, and placed somewhere for future training or whatever other functions, okay? All these functions require a lot of computation. We like that at DELL. Storage and networking, we like that at DELL too. Multimodal operation, that's where these prompts go from being just pieces of a text stream for natural language processing and start moving into the world of computer vision and stuff. So you start adding different types of media, audio, video, point clouds, whatever. You know, what happens is this data, these very small 10-byte tokens become hundreds, tens of kilobytes to 100 of kilobytes tokens. And so this embedded representation goes 10x that. So now you have megabytes of embedded representation around it. So lots of data. I mentioned multimodal. This is a slide from Andrew Ng that I got through NVIDIA. And it, you know, basically shows that as fast as this world is growing, the multimodal world is growing faster. There are some absolutely astounding things that are going on with these multimodal models that, you know, quite frankly, I didn't think were going to happen in AI ever. And they're already doing them today. So models like Lava, Dino, Lisa, you know, they're really, really, really taking off. This is a slide that Jensen Huang presented at GTC. And it basically said, hey, you know, pre-training, which is the art of training a model, the top part of that CI/CD process, I said, you know, has a fairly linear computational requirement and a fairly linear intelligence response to pre-trained models, okay? What's happening now, though, is that you know, there's a lot of what is commonly called fine-tuning. I don't like that, but model customization, where you take this pre-trained model and then say it's a llama model from Meta, and you add layers to it and additional training data to focus it on a particular use case. So you're balancing generalization with accuracy here. So this is happening quite frequently. All our customers are doing it today. But something new has started, which really picks us up. So instead of doing this in offline training cycles, right, even this post-training scaling is done in an offline cycle to train the model. We're now to something called test time or inference time scheduling. So don't know how experienced you guys are with AI, but you know, training is training the model to perform useful functions. Inferencing is using the model to do useful work, okay? And, you know, you have a problem with generative approaches where you have something called hallucination, where the model can get the wrong context and give you a quite confident wrong answer. We've all experienced that playing with chatbots. It used to be much more frequent than it is now. One of the reasons it's not as frequent now is this long thinking test time scaling. So what this is that the model talks to itself or talks to another model. So it gets a prompt, it runs it through the RAG, it gets the right content, it decodes an output, a response, and then it takes that response and it asks itself, through a process called reflection, or it asks another model, did I get this right? And it compares its input with its output, and it makes a judgment call, and then it repeats this process. It may repeat this process 30 times before it provides a response back to the end user. That generates a massive amount of data, and one query becomes 30 queries, so it also generates a lot more computation. So all this stuff in training is really cool. I love my data science friends that are really good at this. This is the exciting part, inferencing, right? And so, this inferencing is done in a lot of different places too. So you start to get things like we hear a lot in NDN, distributed systems start to show up in other capabilities because of the data and computational intensity. Training is usually done in a monolithic cluster that's usually in one location, although people are building giant data centers and tying them together now, but still, it's done in a data center in a very, very curated environment. So trends in AI. So the prompt links are extending. I think they're up to like 256,000 characters. This is pretty hard because the prefill is quadratic in complexity. So as the prompt goes from 1,000 characters up to 256, or 1,000 tokens to 256,000 tokens, this quadratically increases the requirements of computation and memory. By the way, it puts a lot of pressure on memory because that's to load all this stuff into memory. And there's something called a KV cache where we don't want to keep redoing calculations. So we cache data from calculations that are the same and just pull it out of a cache. Improvements to fundamental model execution. So like I said, higher dimension, speculative decode, KV caching. These are all things to make the models work a lot better and work more accurately. Modality expansion I've already covered. We're going to different types of model. Small foundation model synthesis. How do I take a big model and make it less general, but very focused on a particular use case and turn it into a much smaller model? The architecture evolution, this was announced, and I've got a slide coming up on this at GTC. On the inferencing side, we're going to something called, NVIDIA calls the project Dynamo. They publicly announced it there. It uses mixture of experts with sort of like a router that decides where the prompt is best served at. Additional model types called state space machines, which really come out of model predictive control. Very, very interesting stuff going on, and this is moving at light speed, how these models are being re-architected. Just look at the DeepSeek thing out of China with the reasoning models. Hybrid discriminative generative approaches, we'll talk more about that. Object middle model-driven AI with digital twins. So digital twins are really good at modeling complex behavior, and they are synchronized with the real world. AI can create control using model-driven approaches. You're going to start hearing a lot about this next year. There's work being done at the NYU with Jan LeCun, also work being done up at Mila with Joshua Bengio on techniques to start using model-driven approaches to really improve the generalization of generative approaches. Synthetic data is finally here. Thank goodness. A lot of these models are all the model's doing is taking input data and then creating synthetic variants of that input data, which goes back into a training routine somewhere. So again, these models are generating lots of data as well. Not all the stuff I showed before, but actually the whole purpose of the model is to do synthetic data generation. You can look at what like Gretel is doing, Gretel AI, and some of the others. And I'm not talking about stable diffusion here where you're doing artistic stuff. They use some of the same techniques, but it's actually different. You're trying to vary a data set based on certain parameters to give you a much richer capability. This turns out to be a lot more cost effective than collecting data from the real world. Concept reasoning. This is, I was very proud of myself. I wrote this slide about a year ago, and it hasn't changed a whole lot. And, when DeepSeek happened, I said, yep, I figured that was coming. So concept reasoning, or you take the tokens and you distill a concept from a list of tokens, and then you manage the concept. You vectorize and embed the concept and then work with concepts versus strictly with tokens. And then distributed and disaggregated inference, we'll talk a lot about that. Okay, so distributed and discriminative hybrid approaches. So, this is a canonical picture of a self-attention transformer, right? This was what the guys at Google did back in 2017. There's nothing that says that all these layers and all these functions have to be in one place. And there's good reasons to distribute things to edges, to other remote sites, because of computational intensity, because of data intensity. You might want to start doing some of these capabilities elsewhere. And it turns out that a lot of people are starting to think about that. So when one of these models does a inference, it has a pre-fill stage where it receives the input prompt and it runs the entire prompt through many, many, many layers, right? And then that fills up something called a KV cache, or it adds data to a KV cache. And it also provides context. And then it starts a decode process. That's producing the output, okay? So that output has to be unembedded, turned back into, real things that humans can understand versus large multidimensional vectors. So that output is here. This, takes maybe 3 or 4% of the computation. If you did it remotely, right, the positional encoding, the input-output embedding, and the RAG, you'll save maybe 5-6% of the computation. You can spread that out over a large number of sites. This is where NDN starts to show up, because you still have to manage a lot of data. This is all one model. It's got one KV cache. It's got other capabilities, and it needs to shuttle that information back and forth between remote sites, and it has to do it very efficiently and in real time, and many times in a semantic manner versus grabbing, hash keys and looking up the right vector. Disaggregated serving, this is what NVIDIA announced. Basically, take this prefill and run it independently of the decode, and have a smart router called a mixture of experts to decide, where do I do prefill, where do I do decode? Is it a remote site? Do I do it on another node? How do I effectively schedule doing the inferencing inside the model? Really interesting. Today, it's all done serially. Prefill comes in, it does all the prefill, and then it starts it masks. It uses a technique called masking. It starts decoding the tokens, which is the response. Okay, this is all done in a very serial fashion today. In the future, it's going to be done asynchronously. Prefill and decode will not happen at the same time. Prefill will fill as KV cache, and then decode will run based on the data that's being put in the KV cache. This is called disaggregated inference serving. You take that one step further. This is what I presented at GTC. And instead of talking about doing it in different computational nodes in a centralized model, you start to do it across a wide area network, into edge sites, into call centers, hospitals, sites that aren't co-located with the data center. Why do we want to do this? First of all, these sites already have discriminative models running in them, okay, that are doing a lot of computer vision, data analytics, decision-making locally, right, clustering, all this good stuff, right? If you take this capability out here, you can start to generalize, and this thing may have a fallout of, say, 5%. You can solve a lot of those 5% with a model that can reason, with a model that has generalized capabilities, so we can make calls on what these anomalies are. Lots of data gets generated, and you have to have a RAG database that's specific to what this edge site is doing. This is already done in models today, that like in Edge today, they're using discriminative models. For instance, retail stores, every retail store has AI running in it now, okay? I mean, literally every one, down to like convenience stores. If you've got a self-checkout lane, it's running AI somehow, okay? That AI is looking for anomalies and matching SKUs to products, okay, to make sure that there's no fraud, et cetera, et cetera. A lot of data is flying around there, and that data is fairly private, all right? It's running, with points of sale systems and all that. And these retail stores all have a requirement for customization. You may be running a promotion here in Dallas with Walmart stores, but be running a different promotion in LA, right, because of inventory levels or customer preference or a variety of reasons. So they tune these models to be local to the store. That is really hard to do, very expensive, lots of manual data science effort. If you replace that tuning with a more generalized capability that's tied to a large language model, you don't have to do near as much tuning here. This thing can deal with the anomalies, okay? So that's why you would do something like this. And what enables it is that disaggregated serving and the model synthesis and the fact that you can tie these existing frameworks together with the generative capability. Modern data management ecosystem. This is a slide that we talked to folks about DELL Data Lakehouse. Data has a semantic meaning, and there's no catalog in any enterprise on the planet that is comprehensive across all the different data that the enterprise uses. So you need something that can, find the data and transform it into something that can be semantically understood. You need to be able to abstract this data. You need to be able to govern it and say, okay, I can move this data, I can expose this data, I have to anonymize this data, I can't move it without it being anonymized, right? So based on policies, you have to deal with governance and data. And then you have to, discover the data, right? You have to have a capability between this data insights and discovery where you can select the right data to either train your model, to operate your model, or, to just do analytics on so your business your business can operate effectively. And then you need insights on top of that. This is really hard to do. As I said, most data today inside enterprises is collected in silos around their business units or their operational units, and they just don't have the ability to effectively manage this data through a comprehensive catalog. So, and I'm just about done, and I'll take some questions if we have time. My view is NDN could be a big part of the answer. You're producing data across a variety of silos. This data is getting consumed over different silos, and AI has made this problem so much more acute than it was before. NDN can be a key component of managing the provenance and security because you know where it's coming from. We're stamping data, we're signing data, right? You have the ability to do, data movement management with NDN and policies. Right, you can do global advertisement. You can deal with it from a name perspective versus IP perspective, so it fits naturally into a semantic framework, right? But the coolest thing about NDN is you can create it as part of your infrastructure, and to manage your models and your AI capabilities. In the last NDN we did in Gaithersburg at NIST, someone presented using this in training, and that's a really cool use case. But training is sort of in four walls, and it's a controlled, curated environment. In the wild world of inferencing, where data is coming in from users across the internet, from cameras, from edge locations, from cars, from anywhere, right? To get to a semantic understanding of what this data is super important. And there are ways to do it. We've been experimenting with years for things and tying it back to NDN. And then NDN can be a substrate that manages, where is this data placed? What is this content? Do we manage it for availability or consistency? As we all know, the CAP theorem in distributed systems don't allow you to do both. So you need to sort of make decisions. Do you want this data always available, or do you want it always consistent, right? Data persistency, how can I implement a policy that archives the right data, doesn't archive the other data, throws away the data that has no use or value, right? Very important, because data has a definitive cost to it. And then, prioritizes it. So that was my last slide. Sorry it took all the way to get to the end, but I think NDN could be leveraged here. It could be a key tool in helping scale these infrastructures into the real world.
I just saw a question on Zoom. If you mind maybe answering it on Zoom.
So I do think this is going to get standardized. Today, everybody is, there are multiple different embedding models. They're out there. OpenAI's created some, Llama's, Meta's created theirs. A lot of things are sort of being standardized on what OpenAI did. But there's a big opportunity to standardize this even more. And so you can look up embedding models. There's a lot of them, but I think what we're going to see is the industry is slowly but surely gravitating to what OpenAI did for vector embeddings. So thank you again. Hope this was useful. And any follow-ups, I'm easy to find. Jeff.White at Dell.com.